Hello viewers. In our previous videos, while dealing with the two-dimensional or the secondary structure of proteins, we came across various secondary structures like the alpha helix or the beta sheets, the turns, etc. Now, what is the criteria to decide which type of secondary structure will form in a given stretch of polypeptide? This problem was worked out by Professor G.N. Ramachandran and his associates, and with the help of various computer models, they developed the Ramachandran plot. But in order to have a clear understanding of this graphical representation that was given by Professor Ramachandran, we have to understand certain basic concepts. So let us start with it. Now we know that the primary structure or the 1D structure of protein is a polypeptide chain. That is sequence of amino acids which are joined together by means of peptide bonds. And each amino acid, it has got the alpha carbon with the carbonyl group and the amide group. Along with these two groups, there's the side chain R, and of course, the hydrogen is also attached to this alpha carbon. So, at the time of translation, the peptide bond is formed between the amine group and the carbonyl group of these two adjoining amino acids. Now we know that the nitrogen in a peptide bond has got a lone pair of electrons. So the carbon nitrogen bond, it assumes a partial double bond character, and thus it becomes more stable. Now the side chains, that is the R, they basically may be quite bulky and they prefer the trans configuration in the polypeptide, because if they are not present in trans configuration, they will generate steric hindrances. That is, the space that is occupied by them, that will hinder with each other. So the cis configuration in which the two are, they are on the same side of the backbone is not preferred. Rather, we have the trans configuration of the R groups. So our polypeptide chains generally have got these R groups of the adjacent amino acids on the opposite sides, that is one above the plane and the other below the plane of this backbone. Now the peptide bond, because of the double bond nature, it does not permit free rotation, so it is more stable. However, in the backbone, the alpha carbon, it provides two joints where rotation or torsion is possible in the backbone itself. So one is the psi bond between the alpha carbon and the carbonyl carbon, and other is the phi bond between the alpha carbon and the nitrogen of the amine group. Now all these atoms of a particular amino acid, they are not present in a single plane. Rather, they are oriented three-dimensionally. That is, if we have to define the geometry of the amino acid, we will need both the distance of the bond as well as the angle between them. So we have got two planes that can rotate about the alpha carbon. Accordingly, the two angles, that is the psi angle and the phi angle, they are possible. So the backbone in the polypeptide chain, we have the phi angle between the alpha carbon and the nitrogen, and we have got the psi angle between the alpha carbon and the carbonyl carbon. Now, the different torsions or rotation of these two planes, see, they are two different planes because of the three-dimensional orientation of the molecule. So, these different torsions or rotations of these two planes, they lead to different types of foldings of the backbone of the stretch of polypeptide. That is, they result in different types of secondary structures of a protein molecule. Theoretically speaking, the psi angle, it can rotate in the clockwise direction. This is the psi angle between the two carbons, and its value may range from 0 degree to 180 degree. So because of this, say here, this oxygen, it has changed its orientation because this rotation over here, it is by 180 degree. So in this manner, this value of psi angle, it basically, its value, it may range from minus 180 degree, because similar rotation is also possible in the counterclockwise direction, and the rotation angle for this psi angle, hence it may range from minus 180 degree to plus 180 degree. That is a complete 360 degree rotation about this bond is possible, about this psi bond is possible. Now similar is the case with the phi angle. Here also its value, it may range from 0 degree to 180 degree in both clockwise direction and anti-clockwise direction. So here also we have got the range of rotation from minus 180 degree to plus 180 degree. Now this possible rotation of 360 degree about both the angles, that is the phi and the psi, it is just a theoretical possibility. Actually, in a polypeptide chain, we have got the R group, the side chain of this alpha carbon, and this R group, because of its structure, it hinders the stability of various angles of rotation. That is, the side chains, depending upon the size, they generate steric hindrances. If they are very bulky, they won't permit the rotation around this particular bond. For example, glycine, where the side chain is just a hydrogen atom, it permits the maximum possibilities of various rotational angles, while the proline, which is structurally the most complex amino acid, it is responsible for maximum steric hindrance. So now we have got a clear understanding that the secondary structure of a stretch of polypeptide, it is determined by the amino acid present therein, because the specific amino acid has got a specific type of this side chain, which regulates the angle at which these two planes they may exist in relation to each other. So what Professor G. N. Ramachandran he did was that he used certain computer models of small polypeptides, and with the help of these computer models he systematically varied these two angles, the phi and the psi, and his objective was to find a stable conformation, that is, in order to determine which all possible angle conformations they will lead to the formation of stable secondary structures. So he plotted these different configurations or different combinations of this phi and psi as a graph, where this phi angle was on x-axis and the psi axis on y-axis. And for the range of 180, these torsion angles, it varied from minus 180 degree to plus 180 degree for both psi as well as phi. So the resulting graph, 0 is in the center. So this resulting graph, it has got 4 quadrants, and the various combinations of these two angles, they define the secondary structure. Like this region, now in this graph, in this plot, the possible or the stable secondary structures, they are defined by the combinations of these phi and psi in the region that is white in color. So the beta sheet structure, whether the parallel beta sheet structure or the anti-parallel beta sheet structure, or the twisted beta sheet structures, and even the collagen triple helix, these various secondary structures of protein, they are uh, favored when the phi is having a negative value, while the psi angle, it is having positive value. So it is in this quadrant that this beta structures, or rather these structures, they are stable. Now however, if both phi and psi, they have got counterclockwise rotation, that is negative values, the polypeptide backbone which forms, it forms the right-handed alpha helical structure, and which is stable only in this range. And the mirror image of this particular, that is where we have got uh, this positive values for here phi, and positive values even for the psi in this quadrant. Here the we will obtain the left-handed alpha helix in this part. So these two types of secondary structures, they are favored by the mirror image of these various uh, torsion angles. Uh, and this left-handed alpha helix, it is a, of very rare occurrence. It is just a small region of these angles which permits the formation of a stable left-handed alpha helical structure. It is because of the steric hindrance, because it has to go the backbone, it has to go many twists and turns. If both these phi and psi bonds, they have to be in the clockwise direction. So this Ramachandran plot, it presents a clear picture of the possible permitted combinations in a polypeptide backbone and also the resulting secondary structures. This Ramachandran plot, it displays the psi angles as a function of phi angles, and this is used to determine the structure of the polypeptide on the basis of the angles in which these phi and the psi bond they rotate, and the degree of freedom that is permitted by the R groups present, or which is permitted, which are stable for various stretches of polypeptide. So this was all about your Ramachandran plot and the related concepts of the dihedral angle, or the uh, what you call the torsion angle, the steric hindrances that are generated by the side chains. So in nature, everything is well planned. And if we actually want to appreciate any point, what is needed is that we should visualize every concept, and that visualization, it will generate a clear understanding.